105 students. This video covers Module 6, Introduction to Solutions and Aqueous Reactions. Again, a reminder that this coming Monday, which is June 2nd, you do not have to go to the in-person class. I will create this video and then send you all the link to the video. I'll try to cover the first 20, 30 or so PowerPoint slides from Module 6. All right, so let me share my screen with you all. So again, make sure you are comfortable in knowing where to find this Module 6. All right, so Module 6, these are some of the learning outcomes for Module 6. A lot. But then most of these things are definitely some review for at least for students who took C101 last semester. All right. These topics, most of these might be reviewed, but I will go into slightly more depth into, for example, how to write down a complete ionic equation, redox reaction, right? How to recognize a redox reaction, how to calculate the oxidation number of different elements in a chemical reaction, and so on. All right. But again, definitely what you've learned in C101 is going to come in very, very handy here for this learning outcomes for Module 6. All right, so let's start with this topic, because again, this chapter is about solutions. All right, so what is a solution? So basically the idea behind solution is, you can read the whole thing, but the idea is, if you have a solution, right, it is made up of solute and solvent. All right, for example, if I add your table salt sodium chloride in water, I go to the kitchen, I pour out a cup of water, dissolve some NaCl, sodium chloride salt, in water. This is going to be my solute, and water is going to be my solvent. All right. And generally speaking, right, what happens is the majority component is going to be the solvent. All right. And the minority component is the solute. All right. For example, if you have ever done the IV thing at hospital, right? Because maybe your body was low in electrolyte or something like that, right? They inject you with saline water, right? So that saline water is most likely less than 1% NaCl solution. All right. Again, there, if you think about this, the solute is a minority component, whereas the solvent water is the majority component. All right. Now, remember, when we talk about solvent, there are lots and lots of solvents. For example, the nail polish remover, acetone is a solvent, right? Alcohol is a solvent, and so on, right? But if someone specifically says the solvent is water, right? And that solution, which has water as the solvent, we call that aqueous solution. Right? For example, in my example, NaCl in water, right? Saline is an example of an aqueous solution. Right? And another thing to keep in mind, right? You might have you read about homogeneous mixture and heterogeneous mixture, right? A solution is an example of a homogeneous mixture. Keep that in mind, and that is why you see this bullet point. Homogeneous mixtures are called solutions. All right, and then depending upon how much solute you have in a given amount of solvent, we can define the solution, right, in terms of its concentration, right? So if you look at this definition, we're saying that how much solute is being dissolved in a given volume of solvent or amount of solution, right? That's called your concentration. If you have higher solute or higher mass of solute, right? Let's say you have two solutions, right? One beaker, second beaker, right? In the first beaker, I have 2 grams of NaCl dissolved in 50 ml of water. In the second one, let's say I have 4 grams of NaCl dissolved in same amount of water, right? Volume of water, then we can say that, oh, the concentration of this solution, right, is stronger than this solution right here, right? And then we have the words for those to define in chemistry. We call the second solution, this second one, which has more solute, as a concentrated solution, right? Whereas the one with the little amount of solute, they are called dilute solution. That's called dilute solution. Now, do keep in mind, right? This is more. If I give you, for example, a solution, if I ask you, oh, is it an example of a dilute solution or a concentrated solution, right? So think about that as compared to what, right? Because if I ask you, is mouse a big or a small animal, right? Most students will not hesitate to say that, oh, mouse is a small animal, right? But then my question to that is, oh, compared to what, right? Because ant is smaller than mouse. A spider, right? Regular size spider, house spider is smaller than a mouse, and so on. That is why whenever we say that a solution is concentrated or dilute, we are comparing two or more solutions and then making that comparison to say whether the solution is dilute or concentrated. All right. All right, now how much solute is dissolved in a given volume or a given amount of solvent or amount of solution, right, can be expressed in different units. All right, so one of the units that we use to express the concentration of a solution, the most famous one that you might have seen, is something called molarity. Right, the molarity is basically how much solute do you have, right? Amount of solute, but that has to be number of moles. Divide that by the what is the total volume of the solution in liters. Then you have expressed the concentration in molarity. In chemistry, right? Anytime you see capital M, right? That is a symbol for molarity. All right. For example, if I have a solution that is 1.0 M, we're saying that, oh, I have a solution that is 1.0 molar, or like that is a solution with 1.0 molarity concentration. Both of them are correct. All right. Now let's use this formula to solve this question. All right. The first question that implements molarity. So it says determine the mass of calcium nitrate required to prepare 3.50 liters of 0.800 molar calcium nitrate. All right. So for this, again, start out with the formula that you know. My molarity formula, which I'm writing as capital M, equals to moles of my solute, which is my salt, calcium nitrate right here, divided by volume of the solution in liters. And remember, how do I create this solution that I'm talking about? Basically, I take that calcium nitrate and dissolve that in water, right? That's what I do. So that's the solution that we're talking about that contains water as the solvent and calcium nitrate as the salt. All right, so the total volume that you create is what we're interested in our denominator. All right, so let's write down the value 0.800 molar equals to moles of calcium nitrate. So that's my question mark because I'm trying to figure out the mass. So my goal is if I find the moles of calcium nitrate, we all are comfortable going from moles to mass by now, right? Divide by volume of solution in liters. Good thing is they've already given my volume in liters. I multiply both sides by 3.50 liters, all right? Now, just to make sure that you're comfortable with the units, keep that in mind. This is molarity, right? The unit for molarity is moles over 1 liter. Now, if I multiply both sides by 3.50 liters, watch what happens. 3.50 liters times 0.800 moles of calcium nitrate is in 1 liter solution equals to question mark, which is my moles of calcium nitrate, which I can write down as N, right? That's the number of moles. If you think about PV equals to nRT equation, N is the number of moles. That's what I just calculated. Now again, if you think about unit analysis, why does this work? What happens? The liter and liter cancel out with, and you are left with number of moles of calcium nitrate. All right. I do the math. I end up with 2.80 moles of calcium nitrate. Last thing is to go from moles to mass. All I do is I take the molar mass of calcium nitrate, which is 164.088. And again, if you want to gram of calcium nitrate in 1 mole. And if you want to round it down to 264 grams per mole, that's probably fine with me as long as have your final answer in 3 sig figs, right? Because all of our measurements, 3.50 liters and 0.800 liter molar concentration, all of them have 3 sig figs. And that is why my final answer is 459 gram of calcium nitrate. That's the mass of calcium nitrate that I need if I want to prepare a 3.50 liters of this much molar concentration of calcium nitrate, 0.800 molar calcium nitrate solution. All right. So now, let's think about this concept called solution dilution, right? Most of you might have seen this equation M1V1 equals to M2V2, right? Or C1V1 equals to C2V2, different version. Again, the idea is the same, right? So let's assume that I poured Coke, a can of Coke into this beaker, right? So let's assume that can of Coke has 25 gram of sugar. All right. And usually a can of Coke is, I don't know, 250 ml or something like that. So let's assume that it was 300 ml solution. Right. So what I can do, right, is I can add, so let's go ahead and add 100 ml of water. All right. And I used to do this a lot when I was raising my daughter, which in 10th grade right now. She started drinking some juices, right? Apple juice, orange juice. I looked at it, right? The sugar content of the juice is very, very high, right? So what I started doing was I started adding water to her juice. She didn't like it at first, all right? So basically, I was diluting the concentrated solution, all right? Now, what happens in my resulting solution? When I add 100 ml of water is the amount of sugar doesn't change, right? The 25 gram of sugar is still the same, right? But I have diluted it by adding more water because now my volume of solution is going to be 400 ml solution, meaning that the number of moles of sugar does not change, right? Meaning that the moles of solute in solution 1, let me call this solution 1, right? This is my solution 2, is going to be equals to the moles of solute in solution 2, meaning 25 grams of sugar in solution 1, 25 grams of sugar in solution 2, right? Now remember, my formula for molarity equals to number of moles over volume in liters, right? That means my number of moles, N, equals to M times V. If the number of moles N are equal in both the solution, this equation holds true, right? M1V1 equals to M2V2, meaning that M1 is the initial concentration of sugar in this solution, V1 is the volume of this solution, M2 is the final concentration of sugar in molarity in solution 2, V2 is the total volume of the solution, which in our case is 400 milliliters. Right? So this equation is called dilution equation, and we'll use dilution equation to see what kind of problems it's going to look like in the next couple of slides. All right, something like this, right? For example, and this is something that chemistry labs do a lot, right? For example, we have a very, very concentrated solution. For example, I have 12.0 molar HCl, right? So this is my beaker 1. or solution 1, right? Its concentration is given as 12.0 molar. Then I add some water to it. All right. I add the water such that the concentration will end up being 0.125 molar. So I'm diluting the solution, right? My M2 is 0.125 molar. All right. So the volume of 12.0 molar HCl is something that I do not know. How much volume do I start out with? I do not know yet based on this question. All right. But what they have given me is the final volume of the solution, which is my V2 of this solution. The idea is again, you add some water. You add some water, you make this dilute solution, right? The first solution was concentrated, right? By adding water, you made the solution dilute, right? To figure out V1, all I do is I use my formula M1 V1 equals to M2 V2. All right, so I just do is plug in 12.0 molar times V1 is my unknown. I'm trying to solve for equals to M2 is 0.125 molar. And my volume is 250 milliliters, 250.0 milliliters. Unit-wise, right? The molarity cancels out, right? V1 will be in milliliters, all right? So V1, if you do the math, you'll end up with 2.60 milliliters. And again, my lowest measurement, for example, this has 3 sig figs, and that is why my final answer also has 3 sig figs. Right? Now remember, the question did not tell me explicitly if they want the volume in milliliters or liters. That is why I have the answer in milliliters. If the question tells you what volume in liters, make sure you convert the milliliters to liters at the very end. All right, now we're going to learn this concept, which is slightly challenging because there are lots of layers to it. All right, so two solutions are mixed together. Meaning that two homogeneous mixtures, right, are mixed together. In the first one, we had NaCl, right? It's a soluble salt, right? In the other one, we had Na2SO4, and they gave us the volume of the first salt solution, and they also gave us the volume of the second salt solution, which is Na2SO4. And they even gave us the concentration, right? Remember, 0.20 moles per liter is the same as molarity. Moles per liter is the same as molarity because the formula of molarity is number of moles over volume in liters, right? Now, what is the question asking me is, okay, if you mix those two solutions, right, what will be the concentration of each ion? So, for example, NaCl has Na plus ion, Cl minus, meaning that when NaCl dissolves in water, it's going to break apart into Na plus Cl minus ion, right? And then the other one has Na plus ion, which is, we're going to see how that changes when we add those together. And also the concentration of SO42 minus ion. So these are my question mark. So I'm trying to figure out the concentration of all these, right? In chemistry, anytime you see a bracket, big bracket around a chemical species, we say that, oh, we are talking about the concentration of that species in molarity, right? That's what we have to figure out, the concentration of all these ions in the final mixture, right? Slightly challenging, but again, let's just work one at a time, one step at a time, and we'll try to get there. All right. So the first step, what I'm going to do is I'm going to figure out the moles of each ion contributed by each solution, right? Because remember, I had two solutions contributed by each solution, right? First ion was NaCl. So this is my NaCl. And my second one was, let me just do that in red. How about that? Na2SO4. Let's use this color. All right. So my goal is to first find the moles of each ion contributed by each solution. Right. Now, first thing, whenever NaCl dissolves in water, right? When it dissolves in water, when I say aqueous means NaCl are dissolved in water, it breaks apart into its cationic form and its anionic form. Right? Anytime after you write this, make sure you balance the charge as well as the number of atoms. Right? For this kind of problem, I think just balancing the number of atoms first and then balancing the charge next will do. Right? For example, I look at NaCl. I have one sodium atom on my reactant side, same thing, one sodium atom. Right? One chlorine atom on my reactant side, same thing, one chlorine atom. Right? Overall charge, I have a charge of overall 0 on my reactant side. On my peroxide, plus and minus cancel out to give me 0, right? But what is this telling me, right? So if you think about it stoichiometrically, right? When we said, it says like 1 mole NaCl, right, yields 1 mole Na plus, isn't it? All right, because this is gonna come important. All right, now based on my question, first thing I'm gonna do is I'm gonna figure out my number of moles of NaCl, right? Because my first solution said I had 50 ml of NaCl at 0.20 moles per liter. So my goal is to first figure out the number of moles of NaCl. Because if I figure out the number of moles of NaCl, I can use this conversion factor to figure out my mole of my Na plus. All right. So to figure out number of moles of NaCl, all I do is take the molarity value, which is 0.20 moles per liter, times multiply that by the volume. All right. Now remember, the volume is given in milliliters. Your job is to make sure you convert that to liters, 0.050 liters. And that will give me the number of moles of NaCl as 0.010 mole. All right. Now, as soon as I find NaCl in my first solution, I can use this conversion factor, right? 1 mole of NaCl yields or furnishes 1 mole of Na plus, meaning that I can just do this. I can just show you the whole thing, right? 1 mole NaCl yields 1 mole of Na plus ion. Right. Do it this way, the mole of NaCl cancels out with mole of NaCl, and I'm left with mole of Na plus. 0.010 mole Na plus. Right, because remember, my goal was to calculate the number of moles of each ion contributed by each solution. So I figured out my Na plus. All right. Now, good thing about this Cl minus, right? Look at this molar ratios, right? 1 mole of NaCl also gives me 1 mole of Cl minus, meaning that in my first solution, I'm also going to have 0.010 mole of Cl minus ion as well. So I'm just going to write down ion here, right? Again, in chemistry, anytime you have plus and minus charge chemical species, those are called ions, right? So I'm done with my first solution. Let's look at my second solution, right? My second solution is slightly different, all right? Now, I don't want to recommend. All right, so if you have sodium sulfate now, what happens? When sodium sulfate, it's a salt soluble in water, right, breaks apart in water into its cationic and anionic form, same thing, yes, it is gonna form Na plus, aqueous, and then it's gonna form sulfate ion. Now, what I recall from my memorization of polyatomic ion is sulfate is a polyatomic ion with a 2 minus or -2 charge. All right. Now, first thing again, now let's first go ahead and balance the number of atoms first, right? 2 atoms of sodium on my reactant side. To make sure I balance that, I'm just gonna put 2 here. So that balances out the sodium atoms, right? SO4, 1 unit on my reactant side, same thing, SO4, 1 unit on my reactant side. Now let's check the charge. Na2SO4 on my reactant side, it has zero overall charge. Zero overall charge. Right? Let's go to the product side. I have two sodium, right? Each sodium is plus one charge. So 2 times plus one is plus two charge here. And then sulfate has two minus charge. And look at that, plus two and minus two will give me zero. And that's how I know that this reaction is balanced, both atom-wise and charge-wise. Now, what is this telling me though, right? Is this important thing? The numerical coefficient tells me that 1 mole of Na2SO4 salt, right, gives me 2 mole of Na plus and 1 mole of sulfate anion. Now, where did I get these numbers from? 2 mole, 1 mole. Remember, these are just your numerical coefficient in the balanced chemical reaction or chemical equation. All right. All right, now I'm going to follow the same step, right? I'm going to figure out the number of moles of sodium sulfate first. Number of moles of sodium sulfate, right? And again, I have been given the concentration of sodium sulfate at 0.40 moles per liter, right? And the volume, if you multiply these two numbers, right, making sure that this ml is converted to liters, that will give you the number of moles of sodium sulfate, similar to what we did here, right, with NaCl. All right, so 0.050 liters times 0.40 moles per liter. Oh, okay, I think I meant something was okay, yes, sorry. 0.40 moles per liter. All right, I do the math, I end up with 0.020 mole of sodium sulfate. Right, but I'm not interested in sodium sulfate. I'm interested in the sodium plus ion and then sulfate anion. Right, so if you follow the same tactic that I showed you here with sodium chloride, what you're gonna find is for Na plus, since 1 mole of Na2SO4 yields 2 mole of Na plus, right? I can just multiply that by 2 times 0.020 mole. That will give me 0.040 mole of Na plus ion, right? For my sulfate anion, since 1 mole of Na2SO4 yields only 1 mole, that is why SO2 minus ion will have the same number of moles as your sodium sulfate. So that's my first step. The first step is the most challenging one here, right? Now, the thing is, remember, you mixed these two solutions, right? That means the 50 ml of the first solution was mixed with the 50 ml of the second solution. That means the total volume changed. So in my second step, let's calculate the total volume because this is the volume you'll use to figure out the concentration. 50 plus 50 is 100, right? ml, which is equivalent to 0.100 liters. 100 ml is equivalent to 0.100 liter. And again, right now, I'm not keeping track of sig figs. Again, right, all I can do is, right, in the end, keep in mind, I go and do my math, right, is assuming that there's a decimal after 50, right, looks like my final answer has to have two sig figs. So make sure you keep that in mind as you are working through this math, right? So my last step for this is basically, because my goal, remember, if you go back to our slide, my goal is to figure out the concentration of Na plus in the mixture, Cl minus concentration in the final mixture, and sulfate ion in my final mixture, right? So my first goal is, again, Na plus concentration is total number of moles, right, in the mixture divided by total volume in liters. Now, if you go back to the video, what I'm going to do is I'm going to add the moles of Na plus from both the solution. All right, my first solution had 0.010 mole of Na plus, and then my second solution had 0.040 mole of Na plus. My final volume, remember, right, was 0.100 liters. Now I do is do my math. I'm going to end up with 0.50 molar. So my sodium plus concentration in that final mixture is going to be 0.50 molar. I'm going to do the same thing with Cl minus. Good thing was only one solution had Cl minus. The number of moles of Cl minus, we calculated at 0.010 mole of Cl minus. Total volume in liters is 0.100 liters. Do the math, you're going to end up with 0.10 molarity or moles per liter, same thing. Finally, my sulfate ion concentration, number of moles of sulfate, which is 0.020 mole. Total volume in liters is 0.10 liters, and this is how I end up with 0.20 moles per liter or molarity concentration of sulfate ion in that final mixture. All right. Again, there are 3 steps, right? You have to think about to solve this question. Definitely, that tells you this problem is slightly challenging. All right. But make sure if you understand as to what's happening here, what are the formulas that we use, right? And the most important part, I think, where students make mistake, all right, is understanding this, right? For example, NaCl dissociates into Na plus and Cl minus when it dissolves in water. Na2SO4 dissolves into Na plus and SO4, 2 minus, right? But then remember, you have to balance the atom and the charge. And that is why I have 1 mole of Na2SO4 giving me 2 moles of Na plus and 1 mole of SO4 and so on, so on, right? All right. The next concept is something called titration. And if you are taking the lab portion, C125, this is something you've already done in the lab, all right? Idea behind titration is basically, if you think about it, practical application, right? In the lab, what you did was you were given a sample of vinegar. I do not know how much sample you're given, right? And which you can buy from Walmart as well. I can go to Walmart and I can buy a bottle of vinegar, all right? Vinegar contains something called acetic acid, which has the formula CH3COOH, which can also be written as, I have 2 carbon atoms, hydrogen 3 plus 1 is 4, 2 oxygen atoms. So anytime you see something like this, right, this is your acetic acid. And this is one of the acids that you have to memorize the chemical formula. So start getting comfortable with it. Right, so vinegar contains acetic acid, right? And acids are known to have sour taste, and that is why vinegar is sour, right? But then if you look at the label that you bought, let's say from Walmart, bought the vinegar, it'll tell you exactly what is the percent, mass percent of acetic acid in that vinegar sample. All right, usually I think Walmart and other stores sell it as 3.3 to 5% mass percent of acetic acid is present in the vinegar sample, right? And how were you able to figure that out, right? In the lab, you're given a sample of vinegar and you underwent or did something called titration technique. And after doing some calculations, you were able to figure out the mass percent of acetic acid or percent by mass of acetic acid in your vinegar sample, right? So basically the idea behind titration is, for example, other example, let's say if I have a can of Coke. So this is my, again, can of Coke, COK, all right? Now let's say I'm a kind of conscious consumer and I realize that, oh, Coke contains phosphoric acid. But then Coke doesn't tell us how much phosphoric acid is added, maybe. All right. So as a chemist, I can figure out the amount of phosphoric acid that is in a can of Coke by the method of titration. All right. So that's the concept of titration. And you can read the whole thing. Uh, what are you doing in the titration? The setup looks something like this, right? You have something called a burette. And then you have a flask, and the flask is where you have your unknown sample, right? In your lab, it was the sample of vinegar that contained unknown amount of your acetic acid, right? Then you add an indicator to it, some of the common indicator that we use in the chemistry lab are phenolphthalein, phthalene, all right, methylurins, and bromothymol blue. I mean, you don't have to memorize these, but these are some of the indicator that we use. Right, so why are we adding the indicator? Because what happens is, right, is whenever you add an indicator, all right, and when both reactants, so you have one of this reactant in this burette and the other reactant in this flask, whenever they both have reacted completely, all right, one extra drop of indicator will change the color, and that's how we know that, oh, both the reactants have reacted completely. And after that we can do some calculations, which we're going to do in the next couple of slides, to figure out the concentration of your unknown, right? Now whatever is in the burette, right, the concentration of that is known, and that is why we call that a standard solution, right? So burette contains a solution, and the concentration of that solution is known, whereas this flask at the bottom contains an unknown solution, and we're trying to figure out the concentration of whatever that is we're trying to figure out in that solution. All right. All right, so this is the problem, definitely important from if you are planning to, if you are taking midterm exam for your lab, and definitely this is a potential kind of question, right? And the question is very similar to what you did in the C125 lab. All right, so it says a 9.762 gram sample of vinegar is titrated with 0.2250 molar NaOH solution. So meaning that if I draw it, I'm going to draw. So this is my stand, all right? Then this is my burette, and then this is my flask at the bottom. Sorry, I'm not drawing it that good. And then you use clamp to clamp these, right? Burettes, so that they do not fall. All right, so it's telling us that 9.72 gram sample of vinegar. So this is where my unknown is, right? So this is where I have my 9.762 gram of vinegar. And then it says it's titrated with 0.2250 molar NaOH solution. And this is where your standard solution goes. This is where I have my sodium hydroxide solution, right? At the beginning, the initial reading of the burette is 0.31 ml, and the final reading when the titration reaches the end point is 36.48 ml. Again, the idea is you use a certain amount of NaOH solution, right, to reach that end point, and which we can figure out by subtracting the final volume minus initial volume. And that will give you the volume of NaOH solution that you used. All right, and that is when the indicator changes color. For example, it might look something like this, right? At the beginning, whenever you added indicator to your unknown solution, it might have been colorless, right? Once both the reactants have reacted completely, right, one that extra drop is going to make that colorless pink, very slightly pink. And that's how I reach my final volume of 36.48 milliliters. Right now, the goal is to figure out the percent by mass of acetic acid, which we can do if we can figure out the number of moles of acetic acid, right? Because from the number of moles of acetic acid, I can figure out the mass of acetic acid, right? After I figure out the mass of acetic acid, oh, guess what? That mass of acetic acid divided by the total mass of the sample will tell me what is the percent by mass of acetic acid in that vinegar sample. All right, let's work through this problem now. All right, so first thing, like I said, I'm going to figure out the volume of my NaOH, right, which we can do it by subtracting the final volume minus initial volume. And then that's going to give me 36.17 milliliters, right? And then now I have been provided with the concentration of NaOH as well. Because they have told me started with a 0.2250 molar NaOH solution. All right, the concentration of NaOH has been provided to me as 0.2250 molar or moles per liter. Right, so from these two values, I can figure out the number of moles of NaOH, right? The first thing, I want to make sure that this milliliter is in liters, 0.03617 liters. And if I multiply the volume of NaOH times the concentration of NaOH in molarity or moles per liter, I'll end up with the number of moles of NaOH is equals to 0.03617 liters times 0.2250 moles over 1 liter. And again, if you think about this, right, this is the same concept that we've been talking about, right? Data given times the conversion factor, isn't it? So data given was the volume of NaOH times the conversion factor. Again, if you want to think about it another way, right? Because remember, molarity had the formula number of moles over volume in liters. If I multiply both sides by V, my formula for number of moles N will end up being molarity times volume. Same thing here. This is my molarity term. This is my volume in term. All right. Whatever way you want to go and approach this problem, it's up to you. If you want to memorize the formula and go this route, be my guest. If you just want to do some unit analysis that I shown here, be my guest. All right. All right. Now, after I do this, then before I move on and figure out the number of moles of acetic acid, first let me write down the reaction. My reaction looks something like this, right? So you have NaOH, which is usually always an aqueous solution because sodium hydroxide is basically this white pellet that you can find in the lab. But what we do is we create a solution, right? To create a solution of 0.2250 molar NaOH, we take that white salt NaOH, if you want to call it, right, and dissolve in water. That's why I said NaOH aqueous, plus my acetic acid sample. All right, now remember, this is the only H that's acidic in my acetic acid. Right, so this is the only H there is. For example, HCl has only one H, right? Whereas H2SO4, it has two H and so on. All right, so think about this acetic acid as having only one H, right? And again, remember, acid plus base, right? Because this is my base, this is my acid. I went over the acid-base reaction is always salt and water, meaning that that H in my acetic acid is going to react with this OH because it's a double displacement reaction, giving me water plus and a salt is formed. NaCH3COO, and this salt is soluble in water. That's why NaCH3COO aqueous. Now the good thing is this reaction is already balanced, right? Now what this is telling me is 1 mole of NaOH reacts with 1 mole of CH3COOH, right? To give me 1 mole of H2 and 1 mole of sodium acetate salt, right? So from this 1 to 1 mole equimolar ratio, I can figure out the number of moles of CH3COOH, which is my acetic acid, is going to be the same as the number of moles of NaOH, which is going to be this my math right here. right? If I multiply this 0.03617 liters times this number of moles of NaOH is going to end up being 0.0081382 moles. All right, 0.0081382 moles. Remember, this is the moles of acetic acid as well, right? Because CS3COOH, we just said that the number of moles of acetic acid is equals to number of moles of NaOH because they are reacting in equimolar ratio. So this is the acetic acid as well. And I can go from moles to mass from my conversion factor of molar mass. All right. Now acetic acid CS3COOH has a molar mass of 60.05 grams in 1 mole. Okay, if I say it out this way, the mole and mole of acetic acid cancels out. If I multiply these two numbers, I end up with 0.488702 gram of CS3COOH or acetic acid. Am I done? No, because my question is asking me for the percent by mass of acetic acid in the vinegar sample. I just figured out the mass of acetic acid in the 9.762 gram sample. So all I do is take that number, divide that by 9.762, times that by 100, and that will give me my final mass percent. All right. So 0.488702 gram of acetic acid. And the vinegar sample had a mass of 9.762 gram of vinegar. You multiply by that 100, that will give you my mass percent. Percent by mass of 5.006%. Right now, again, if you look at this, I included 1, 2, 3, 4 sig figs because if you look at all my units, right, they have 4 sig figs 1, 2, 3, 4, 1, 2, 3, 4, and so on. All right, now keep in mind, right? You might be tempted, oh, but this only has 2 sig figs. But remember, if you subtract 36.48 ml and then subtract that from 0.31 ml, remember the technique I taught you? This is where I draw the line, right? And 1.36. Meaning, whenever I report this, I should have 1, 2, 3, 4 sig figs. And that is why your final answer will end up having 4 sig figs as well. Okay. All right, 1, 2, 3, 4 sig figs. Right. And hopefully, like if you're taking the C125 lab, this is more like a review for you, right? Very important from exam one point of view, which is right around the corner. All right. And there'll definitely be a couple of problems from titration for sure. All right. So now, if you think about that, our stoichiometry, right? Whenever I give you problems for stoichiometry for exam 0, right? What was given was mass of reactants, right? And or mass of product. And then you're asked to find the other one, right? So the mass one might have been given in milligrams or grams, all right? But in our solution stoichiometry, what happens is these kind of problems contain the amount of products or reactants in liters, right? And you'll be asked to figure out the maybe the volume of the fine products or the reactants, right? Again, this looks weird, but again, it's if you look at when we work through this problem, it's not going to be that bad, right? For example, what I mean by that is the solution stoichiometry problem looks something like this, right? So you have a reaction, right? Potassium chloride is reacting with lead 2 nitrate, right? Giving you lead 2 chloride and potassium nitrate. right? This is an example of a double displacement reaction or exchange of partner, all right? Now, but if you look at this, if it was the stoichiometry problem from 1 week before, it might be more like 5 gram of KCl reacts with 10 gram of lead to nitrate, right? And what is the mass of PbCl2 salt formed, or something along that line. And but if you look at this question, it's more like it's asking us what volume of this certain concentration of KCl solution will completely react with certain volume and the molarity concentration of the other solution and so on. So that is why this is called a solution stoichiometry, because we are looking at solutions and also we are talking about the concentration of the solutions here. All right. So if you read this question, we can paraphrase, right? This question as these are the given values, right? Volume of the solution, molarity of this solution, and the volume. All right. We have been given the molarity of the KCl solution. Then our end goal is to figure out the volume of the KCl solution. Right. So first thing I'm going to do is I'm going to follow this plan. So this is my plan. Right. Is I'm going to use these two values, the volume in liters and then the molarity value of the lead to nitrate, to figure out the moles of this lead to nitrate. After I figure out the moles of this, I can see that 1 mole of lead to nitrate reacts with 2 moles of KCl, right? So use that stoichiometric ratio to figure out the mole of KCl. Once I find the mole of KCl, I've been given the molarity of KCl. So use the molarity and the moles of KCl to figure out the final volume of the KCl solution, because that's our goal, to find the volume of KCl solution in liters. So let's follow this plan. If we follow this plan, this is what it's gonna look like. Again, our first goal is to figure out the number of moles of lead to nitrate. And again, number of moles is molarity times volume in liters, right? Molarity of this solution is given to me as 0.175 moles over 1 liter times the volume is given in 0.150 liters. Multiply these two numbers, I end up with 0.02625 mole of lead to nitrate. All right. Now, if you look at this reaction, it's telling me that 1 mole of this is reacting with 2 moles of KCl. And that means you need twice the number of moles for KCl. That is why if I want to find the number of moles of KCl, all I do is take that 2 times 0.02625 mole. And that will give me the value 0.0525 mole of KCl. All right. Now, they have given me the molarity of KCl, right? So if you look at this question, they told me that, oh, the KCl solution had a concentration of 0.150 molarity or molar. So I have that value, 0.150 moles per liter. For KCl, the concentration was given to me as 0.150 moles over liter. Now, our end goal is to figure out the volume of KCl solution. If you want to go ahead and use the molarity formula and plug that in, be my guest, all right? Or if you want to do something called unit analysis, right? So data given is going to be this 0.0525 moles of KCl times my conversion factor is going to be this, which tells me that 0.150 moles of KCl are present in 1 liter solution, or 1 liter KCl solution. Let's be explicit. If I set it up this way, my moles of KCl cancels out with moles of KCl, and I'm left with volume of KCl solution in liters. And that's how I get my answer as 0.350 liters of KCl solution to 3 sig figs. Right? Again, what I did was follow this plan, a roadmap, whatever you're gonna call it. I used the molarity value of lead 2 nitrate and the volume of lead 2 nitrate to give me the moles of lead 2 nitrate. After you figure out the moles of lead 2 nitrate, I see that, oh, this balance reaction tells me that 2 moles of KCl reacts with 1 mole of lead 2 nitrate, right? And that is why I can use this stoichiometric ratio to figure out the number of moles of KCl. And finally, after I have the moles of KCl, use that and the concentration of KCl in molarity to figure out the volume of KCl solution in liters. All right, now let's next 5 or 6 slides. It's mostly conceptual, so I'm gonna kind of uh, fly through it. So try to keep up with it. And again, if you're confused, definitely you can read the e-textbook from your mastering chemistry, right? So now we just talked about acids and bases. So let's kind of understand what the heck do those terms mean, all right? So the idea behind acids, right? So again, you might have learned about Arrhenius theory of acids, Bronsted-Lowry theory of acids in C101 and so on, right? The idea is when acid dissolve in water, they ionize, meaning they form ions. For example, what I mean by that is if you have an acid, I'm just going to call that acid XX, right? When it dissolves in liquid water, it ionizes, meaning this and this part, they separate. The S2 is going to grab that H, giving you this S3O plus, which is called hydronium ion. One of the polyatomic ion you have to be comfortable with. And then whatever is left is my X minus. That comes from here. And that's what all the acids do, right? They react with water to form hydronium ion and then the anionic part that's left over from the acid, right? Now, if you have a strong acid, and I'm going to show you a list of strong acids that you have to memorize, all right? Almost 100% of the acid react with water to form the product that I showed above. For example, HCl is a strong acid, meaning that all of HCl is going to react with water to give you S3O plus and then Cl minus as your answer, as a product, right? But if you have weak acid, what's going to happen is, for example, HF is an example of a weak acid that is shown in red. HF is an example of a weak acid. It reacts with liquid water, all right? And I'm going to show you something called equilibrium error. The products are going to be the same, right? Same way I'm going to write my product. One of the products is going to be hydronium, similar to this hydronium. And then whatever is left, which is my F minus, right? But what happens is only maybe from anywhere from 0 to, let's just say, I'm just going to give a number, 5% of HF molecules will react with water. The other, let's just say 95%, they stay in their original form, which is the HF form, right? And that's what all the weak acids do. They do not ionize completely in water. And anytime you have weak acid, we saw this something called equilibrium error, right? Saying the audience that the reaction has not gone to completion, or my product contains lots of my starting material as well, All right, and I'm going to show you in the next couple of slides. There's a very nice depiction pictures that shows this concept pictorially. All right, but there goes your strong acids and weak acids. All right, so this is what I mean. For example, we just said that HCl and water, they are strong acids. All right, can you fix this? This shouldn't be R, it should be an arrow here, like a reaction. 100% of this HCl will react with water to form hydronium ion and then chloride ion, right? So this was my Ha. So think about this as a small gray sphere as H, and then this large, I don't know, that's greenish color, I don't know, greenish yellow, is my A portion. So this is my A portion. So that's my acid right here, right? This is my hydronium S3O plus. These are my hydrogen atom, hydrogen atom, hydrogen atom, and the red sphere is my oxygen atom there. And then that, like I said, that greenish yellow is my A part of my acid. Right? Now, let's say I run through this reaction in the lab, and if I am able to see what's going on in my final product box. So I'm just gonna call this my product box. What I'm gonna see is I'm not gonna see any of my starting material HCl. Look at that. This is my S3O plus here. That's my product. This is my Cl minus. This is my S3O plus. This is my Cl minus. S3O plus. And then Cl minus. And that's what happens if you have strong acids, right? But if you have weak acid, what's this? If you have hydrofluoric acid, right? And then yes, the product are going to be the same, all right? An arrow, equilibrium arrow, right? Hydronium ion as one of the product, and then whatever is left from the acid. The products are going to be the same, but let's look at our product box now. If we look at our product box, look at that. I still have my HF that's left over. HF, HF. Yes, I do have my product right here. S3O plus, and then F minus. But HF is still left. HF is still left. So it's like, it looks like what's this telling me based on this box? What I see, right, is out of 1, 2, 3, 4, 5, and then 6 HF molecules, only 5 have reacted. Sorry, only 1 has reacted with water to give me the S3O plus and F minus. The other 5, they've remained in their original HF state, or they have not ionized or dissociated into ions. So whenever someone says something is ionized, it's the same as someone telling you, oh, it breaks apart into ions or dissociate into ions, right? Plus charge, minus charge. These are your ions, right? And that's how you can conceptualize strong acids and weak acid. And this is the list that I was talking about, which you have to memorize for this course. And make sure you know how to come up with the chemical formula of all these acids or the other way around, right? Same thing with weak acids. These are your common weak acids. Make sure you know the chemical formula of all these weak acids as well. And acetic acid is the acid that we just worked on for the titration problem. All right. Now, bases is the same concept, right? Similar to acids, we do have strong bases and weak bases, but then conceptually speaking, we're going to define them in the same way. And then, but we're just going to talk about H plus now, or hydronium ion. Whenever we think about base, we're going to think about hydroxide anion. So base forms hydroxide ions or anions in water. For example, if you have QOH base, 100% of this is going to dissociate into the cationic form and then anionic form. All right, that's why it's called strong bases. Whereas if you have weak bases, like ammonia is an example of a weak base. In the next slide, we do have a list. Weak base. Again, the reaction will also produce OH minus. All right. But what's going to happen is the ammonia has to react with water to furnish the OH minus. First thing, that's what weak base do. And the other thing is, again, I'm going to write down instead of this kind of arrow, I'm going to use the double-headed arrow, like this kind of arrow, right? That's telling the audience that, oh, my product box is going to have lots of my starting material left over. All right. So basically, only a fraction, maybe you're talking about maybe again 0 to 5% or less than 10% of the ammonia will react with water to form the OH minus or the hydroxide ion in water. And these are the list of the strong bases and the weak bases that you have to memorize. And again, if you look at these, most of these, for example, lithium, sodium, potassium, rubidium, cesium, these are group 1A metal, right? Group 1A metal. So the hydroxides of those metal are considered strong bases. And then calcium, strontium, and barium, these are your group 2 metals. And finally, your weak base. Ammonia is an example. I'm going to write down a couple of other example as well, right? Is CH3NH2. If you look at this formula, it's pretty similar to NH3 formula, right? Look at this, NH2 is here as well. And then CH3, CH2, NH2. So this class of bases are called amines, A-M-I-N-E. Or amine, I don't know how to pronounce it, amine or amine, right, in organic chemistry, and these are considered your weak bases. So I'll be comfortable with these three weak bases in per C105. All right, now we're going to talk about this concept called electrolyte, right? Since we talked about salt dissolving water to give us aqueous solution, we talked about strong acids, weak acids, strong bases, weak bases, and so on. All right. This leads to our concept called electrolyte. All right. So now you should have learned, or someone might have told you, right? Oh, Gatorade, drink Gatorade, it contains electrolyte. But have you ever thought of what the heck is that electrolyte? Right? What am I drinking whenever I'm drinking Gatorade? Because they tell me drink Gatorade to replenish electrolytes in your body, right? Yes, Gatorade, Powerade, they contain electrolytes. So easy way to think about electrolytes are dissolved ions in water. That's it. If you have dissolved ions in water, that's called your electrolyte. That means Gatorade contains ions such as K plus, sodium plus, Cl minus. So these are dissolved ions, right? And that is why the Gatorade Powerade drink are, are known to contain electrolytes, right? So now let's distinguish strong, weak, and then non-electrolyte. So first thing before I talk about that, let's move one slide forward and then let's look at the pictorial depiction, right? Some of the chemicals, when they dissolve in water, right? And if I form a complete circuit, right, I'm able to light the bulb. For example, the very right hand side, this solution contains sodium chloride solution, right? After I create a sodium chloride solution, if I complete this circuit, this bulb will light up, right? It's kind of bright, all right? Now, if I take some acetic acid and dissolve it in water, what's going to happen is this bulb is also going to light up. All right. But look at the brightness level. This brightness level is not as strong as the one on the right, right? And finally, we have some solutions, all right? It is in the liquid form, right? This is basically sugar. Sugar that has been dissolved in water, all right? Now, if you complete the circuit, the bulb will not light up, right? So easy way to think about this is the one that lights up the bulb the most brightest. Those are all called your strong electrolytes. The one that lights up the bulb but is not as bright, all right, that's called a weak electrolyte. And the one that does not light up the bulb at all is called your non-electrolyte. Right? So here are the definition. The idea behind all this, right, is basically for electrolytes, you should have ions in solution, meaning that the salt of interest, salt or anything else, right, chemical of interest, should dissolve well in water and then dissociate completely. For example, sodium chloride is a strong electrolyte because it's gonna dissociate into sodium plus and then chloride minus ion. And that's why this is an example of a strong electrolyte, right? When it lights up the bulb, that's basically someone telling you it conducts electric current. When electric current is conducted, right, via wire, flow of electrons, and that is when the bulb lights up. Right? And the last and the most important one is examples of strong electrolytes contain soluble ionic compounds, also strong bases. That means strong bases, strong acids, and then soluble ionic compounds. In the next 3 or 4 slides, we will learn how to determine whether an ionic compound is soluble or not. Right? But then all soluble ionic compounds are considered strong electrolytes. Right? Example of weak electrolyte, for example, weak acid, which was acetic acid, they do dissolve in water, all right, or they may not, but then they do not dissociate into ions completely. In our strong electrolyte, dissociation happened completely. So basically NaCl dissociating into Na plus and Cl minus completely. Whereas here, the dissociation is only partial. Then since they have low conductivity, right? Since you have low amount of ions in that solution, that is why there is low conductivity. And examples of weak electrolytes include weak acids and weak bases. And finally, non-electrolytes are some salts or any chemicals that dissolve in water, or all right, or they might not dissolve in water, but even they do that, they do not dissociate into ions. For example, C12H22O11, right? It dissolves in water. You throw sugar in water, you stir it, it will dissolve in water. But what doesn't happen here is the C, H, and O, they do not break apart into ions like Na plus and Cl minus. They are one unit together. They do not break apart into ions, and that is why they are not capable of conducting electric current. All right, that's what it means by no or negligible conductivity. And I hope this picture helps you clarify some of these things. Right now, again, these are just a recap of what I just talked about. All right, now it's easy to figure out what are strong electrolytes and weak electrolytes. Right, like I said, strong electrolytes are going to be examples of strong acids, strong bases, and soluble ion compounds. For example, if I look at this Na3PO4, in the next 2 or 3 slides, we're going to learn that this salt is soluble in water. This is my ionic compound, soluble in water, meaning that it's going to be an example of a strong electrolyte, right? Strong acid, for example, H2SO4 is an example of strong acid. That is why it's strong electrolyte. Strong base, calcium hydroxide, is an example of a strong electrolyte. Now, weak electrolyte are weak acids and weak bases, the examples of which you have to memorize from the last 3 or 4 slides, all right? And last one, the examples of non-electrolytes contain sugar molecule, right? Sugar, glucose, right? Methanol, ethanol are some of the examples. So let me write down 3 or 4 more examples. That way you see a pattern, right? So our sugar formula that we had for that, right? Our picture had C12H22O11. C12H22O11. That's my sugar, right? So whenever it dissolves in water, even though it dissolves in water, these do not break apart into ions. This is one unit, right? That's why non-electrolyte. Other examples is glucose, C6H12O6. Other example is alcohol, ethanol. So you might start seeing the trend, right? Usually, not all the time. There are exceptions, right? Whenever you have carbon, hydrogen, and oxygen containing compound, and there isn't any ionic polyatomic ions in there, those will, most of them, generally speaking, will be your non-electrolytes. And the other most important example, right? The most famous one is water, meaning that water, for example, let's say if I go and drink water from my tap water, all right, that tap water contains some lead ions, it contains some sodium ions, it contains some chloride ions, and so on. That means if I take that ion, complete the circuit, the bulb will light up, right? But somehow, if I'm able to remove all the ions, right, if I have only water molecules present in that sample, which I'm going to call it as pure water, is an example of a non-electrolyte. Right, so make sure you're comfortable with these examples of non-electrolyte. All right, so a couple of minutes ago, I said something about soluble ionic compounds. All right, so we're gonna look at something called rules, solubility rules. That helps us. Sadly, you do have to memorize this for C105. All right, it helps us figure out whether a salt is soluble in water or not. All right. For example, let's say these are the rules that you're going to memorize. And then if I ask you something like, oh, I had this salt in lab, NaCH3COO. And if I ask you, is this soluble or insoluble in water? Here I'm assuming that you'll have memorized all the rules. And if you look at our first rule, it says all common compounds of group 1A, right? That contains sodium. Oh, right here. This contains sodium, and that is why this says are soluble in water. That's how I know this is soluble in water. If you look at even rule 2 points out that this NaCH3COO is soluble in water because it says all common nitrates, acetates, CH3COO minus. Look at this. Isn't this my CH3CO or acetate salt? And that is how I know that this is soluble in water. Right? Now, if I give you something like, let's say, Hg2Cl2, and I hope you recall, right? I told you what is this Hg2, right? A week and a half ago, all right? So make sure you go back to your notes and then refer to that, right? So I said something about, oh, some of these elements in periodic table, right? They exist as diatomic form. For example, have no fear of ice cold bear in nature, right? For example, we said that sulfur, right, exists as S8, meaning that 8 sulfur atoms combine together in nature. Whereas some of this mercury, they exist as a dimer, Hg and Hg, that are bonded together. And that is why you see Hg with a numerical subscript 2. So it exists as dimer as well. That's an example, right? So if someone asks you Hg2Cl2, is it soluble in water or not? Then I look at my rule. Number 3 tells us all common chlorides, right? Cl is the salt, Cl minus when it dissociates, right? Okay, are soluble. Okay, I might be tempted to say that it's soluble, but then it says, look at the exception, those of Ag plus, Pb2 plus, Cu plus, and Hg2 2 plus. This is my Hg2 2 plus salt, and that is why this is insoluble in water. Right? So these are the rules that you have to memorize. There's one more page. Right? So go over these rules, and then if you want to work on these, I'm going to give you name some of these salts, right, for you all to work on, and then you can figure out whether they are soluble or not. And pause this video as soon as I write down this thing. Pause the video first. This is the salt. Right, pause the video, right, and then try to use the two slides of rules to figure out whether these salts are soluble or not. All right, I'll give you answer in like under 10 seconds. All right. All right. So if you follow the rule, this is going to be insoluble in water. Al2SO3 is going to be insoluble. This is my sulfide. This is my phosphate, insoluble in water. This phosphate, phosphate on the other hand, is soluble in water. Ammonium sulfate is also sulfide, not sulfate, sorry, ammonium sulfide is soluble in water. AgCl is insoluble in water. And finally, PbI2 is also insoluble in water. Let me double check with PbI2. My rule for that says yes, PbI2 is also insoluble in water. So that means if you answered all this correctly, means you know how to use these two PowerPoint slides, and assuming you've memorized and able to conclude whether a salt is soluble in water or not. All right. The next concept we're going to talk about is something called classes of chemical reaction. I have started talking about that, right? I talked about combustion reaction, right? We talked about combination reaction. We talked about acid-base reaction, right? So now we're going to go over some of the other reactions that are in the list, all right? Now, all these reactions can be broadly classified under these two umbrellas: double displacement and then redox reaction or oxidation reduction reaction. Right? So let's look at our first, some of these double displacement reactions, and I'll provide you with some example. All right, so we have three reactions under double displacement reaction, and I'm going to go through these three first. All right, so precipitation reaction, acid-base reaction, gas forming reaction. All right, precipitation reaction, we'll look at this example. All right, I'll give you this example of precipitation reaction. So first thing, precipitation reaction, again, is an example of a double displacement reaction. So if I have a soluble salt, right, so again, I haven't balanced the reaction. Make sure you balance it. But again, here, I'm just trying to show you why is this called a precipitation reaction, right? So if you start out with soluble salts, AgNO3, I write down AQ is telling me that this salt is soluble in water. This salt right here, sodium chromate, right? Make sure I, sorry, not sodium, yes, sodium chromate, CHROMATE. And then you're going to see that in the next slide as well, right? So not to name wise, you don't have to worry about it because it has told you like this is sodium chromate and so on. When these two react, what's going to happen is, again, two soluble salts, when they react, all right, you're going to see a clear solution as well, but then you're going to see some solid forming at the bottom of your reaction vessel, meaning what it looks like. This is your silver nitrate, and then sodium chromate is this right here. You see both of these are clear, meaning that the salts are soluble in these. Then if I mix these two, right, this is what I form. You do see a clear solution up on top, but then I do see some undissolved solid. And that undissolved solid at the bottom, it's called a precipitate. Since precipitate formed, we call that precipitation reaction. And that is why this is an example of a precipitation reaction. And again, make sure you balance the reaction. I haven't balanced it for you. All right, make sure you balance the reaction. All right, the next one is acid-base reaction. I don't have to go through this. I already talked about it. All right, if you have an acid, really quickly. Right, if you react that with base, the product is salt and water. Make sure you are able to write down the product. And again, remember, these are both examples of double displacement reaction where there is exchange of partner, right? For example, this Az now partners with CrO4, right? Whereas NO3 partners with Na. Since they exchanged partner, that is why. Same over here. My H here partners with OH, whereas my Cl on my reactant side partners with calcium to form the product. And that is why these both are examples of double distillation reaction. Right? The second one, again, it's an acid-base reaction. The product is always salt and water, right? And makes sure you balance the reaction. And the last part of this double distillation reaction is called formation of a gas. Right? So let me write down an example of that. The formation of the gas looks something like this. So if I have sodium bicarbonate, sodium bicarbonate salt, if it reacts with HCl, which is my acid, I end up with sodium chloride plus H2CO3. Now, as you see, again, this is an example of a double distillation reaction. Na partnering with Cl, right? And then HCO3 partnering with H to form H2CO3. So there's exchange of partner. That's why this is an example of double distillation reaction. But why or how this is an example of a gas forming reaction? So what's going to happen is this H2CO3 is called carbonic acid, which is unstable in its aqueous form. It's going to decompose into liquid water, and then carbon dioxide gas is given off. So since you form this gas, that is why this is called the gas forming reaction, our third type under double displacement reaction. All right. So now let's go back to our first reaction where we worked on the precipitation reaction, right? So this was our precipitation reaction. Silver nitrate reacting with sodium chromate, all right, to give us silver. Oh, I should start saying the Roman numeral as well, right? So let's be explicit, right? And where do I have that bracket here? Ugh, let me delete that bracket. So there shouldn't be a bracket here because this is silver 1 nitrate. Sorry. So silver 1 nitrate giving you silver 1 chromate and then sodium nitrate as a product, right? Now, there are three ways to talk about these reactions whenever it's in an aqueous solution, right? Whenever you saw all the reactants and products in their undissociated form, right? Keep in mind, right? Silver nitrate is its aqueous in solution. If I zoom in, right? Remember, this has dissociated into silver ion and nitrate ion in water, right? But whenever I run a balanced chemical reaction, I do not show that. So your molecular equation shows reactants and products in undissociated form, right? None of these were dissociated. That is why this right here is an example of a molecular equation, right? And then every molecular equation must be balanced, and that is why you see these numbers, numerical quotient in front. This 2 balances out the silver atoms and so on. This 2 balances out sodium and so on, right? Now the next one is called the total or complete ionic equation. So now if I take this reaction, all right, if I break them into their counter cation and anions, all right, meaning that the soluble salts, right? If you have that and you break them apart or dissociate into the cationic form and anionic form, and if you show it that way, we call that total complete ionic equation. For example, you have silver nitrate, right, breaks apart into Ag plus and then nitrate ion. That's why you see this Ag plus and nitrate ion. Same thing with sodium chromate. It's a soluble salt, right? How do I know that? Because we just talked about the solubility rules. My solubility rules says that metal 1 chromate, A group 1 metal chromate, sodium, is soluble in water, meaning this can break apart into sodium plus and then chromate anion, right? If you have solid or the precipitate, meaning that they do not break apart into anion, right? Those are ionic compound that are not soluble in water. Leave them as they are. And finally, sodium nitrate is a soluble salt. That is why break them apart into their ions, right? This goes back to what I worked on very beginning, right? Whenever we work through this problem. So let me go back somewhere. I wrote it down. Whenever we figure out the number of NaCl, yeah, right here. So if you go back to this problem, right? If you recall, what I did was I broke apart this sodium sulfate, right? Salt, like this. I took this sodium sulfate salt, which are soluble in water, and I said, oh, it breaks apart into this plus sulfate anion, because this salt is soluble in water. And that's what you do for your total ionic or complete ionic equation, which is right here. Right now, whenever you have your total complete ionic equation, right, keep in mind the atoms and the charge must balance out, right? For example, in my reactant side, the overall charge is 0. Same thing over here. Now let's check. I have 2 plus charge on silver, 2 plus charge on sodium. So 2 plus charge plus 2 plus charge, that's 4 plus charges. Let's look at the negative charge. 2 negative charge, 2 negative charge. That's negative 4 charge. Plus 4 charge, minus 4 charge. That's why this is overall 0. And the same thing will happen on this side of the equation as well. All right, that's really important for a total complete ionic equation. All right. And finally, for the net ionic equation, what you do is after you write down the total ionic equation, all I do is I cancel out the ions that are the same on both the sides. I see that I have nitrate ion on both the sides, so let's cancel that out. NO3 ion cancels out with NO3. When I say both sides, means reactant side and product side, if they are the same, right? I have 2 sodium plus, 2 sodium plus. I can cancel them out, right? So the ions that cancel out are called spectator ions. So please write that word out. Spectator ions. Meaning if I ask you what are the spectator ions in this reaction, you'd say Na plus and then NO3 minus are your spectator ions. Right? So if you think about this, your spectator ions right here. So if we go back to the reaction that we're looking at, right? This is our reaction. Will be present in the clear solution on top of the precipitate in their dissociated form. So there is going to be your Na plus and then NO3 minus, soluble salt, right? In that clear solution. All right. So those are called spectator ions, right? So now, after you cancel out the spectator ions, whatever is left, right? So I have 2Ag plus left, a CrO4 2 minus left, giving me Ag2CrO4. What you have is called the net ionic equation, because this is the only place where the chemical change has happened, right? The formation of a new product as a solid. So that basically formed when Ag plus reacted with chromate anion to form silver 2 chromate. Sorry, silver 1 chromate. Sorry, my bad. Right now, if you think about charge wise and number of atoms wise, this must be balanced as well. For example, I have 2 silver atom on my reactant side, 2 silver atom on my product side. CrO4, CrO4. Charge wise, 2 times plus 1 is plus 2 plus minus 2 is 0. Overall, on the product side, that's also 0. And that's how I write my net ionic equation. Right? So again, whatever I told you, please, it just follows that. And I'm going to work through one problem based on that. That way you'll get a hang of it. And this is the procedure that you follow that I just told you about, right? As to how to write down the total complete ion equation, what are the spectator ions, how do you cancel out the spectator ions, and how to write down the net ion equation. So this is the route that you follow to get there, right? The final step is it says if neither product will precipitate, right? Because in our reaction, we did form a precipitate, which was our solid here, right? And we said that, oh, there is no reaction after the arrow. That's what we're going to write down, right? So based on these couple of three slides that we just talked about, I'm going to work through these couple of examples that you'll get a hang of it, all right? I'm going to work through number 1 and 2, and you can try number 3 yourself. All right, so the question is going to look something like this, right? Write the molecular, total ionic, and net ionic equation for the following reaction if they occur. If they do not occur, you just write down no reaction occurs. All right, so if you're taking C125, this is going to be very important for your C125 midterm as well. All right, so let's start with the first example, silver fluoride plus sodium phosphate. Silver fluoride plus sodium phosphate. Right. And then I should have been more, sorry, I should have been more explicit there. That should have been silver 1 fluoride. Right. So this is my silver 1 fluoride. That is soluble in water. And how do I know that? Based on the solubility rules, right? Reacted with sodium phosphate. Make sure you know how to write down the chemical formula of these ionic compounds. Then again, remember, this is an example of precipitation reaction. This is an example of a double displacement reaction, meaning that this AZ is going to partner with phosphate, right? And then F is going to partner with sodium in our product side. So right on the product, I'm going to get sodium fluoride, which is also soluble in water. Plus, I have silver 1 phosphate, all right? Silver 1 phosphate, if you recall the crisscross method, it's going to look something like this. All right, now if you look at the solubility rule, it tells me that silver 1 phosphate is insoluble in water. So this is my precipitate. All right, so that's my first step of writing down the molecular equation. The next step is I'm going to balance this reaction out. If I have a quotient of 3 here, that's going to balance out the silver atom. All right, so I have 3 sodium on my reactant side, meaning I'll need 3 here. And that should balance everything out. All right, so this is my molecular equation. The next thing I'm going to do is I'm going to write down my total ionic equation or complete ionic equation. Again, the idea is I'm going to break these soluble salts into their cationic form and anionic form. All right, so I have 3AgF, 3Ag plus, and then 3F minus, because this is a soluble salt. This is what it breaks apart into. Plus, I have sodium phosphate, right? I need 3 of this sodium to balance it out. And this part is where the students struggle with as to why I have 3 in front, right? Because remember, I have to balance this out, the number of atoms. And that is why I have a numerical coefficient of 3 in front of that sodium ion, right? And then I have phosphate anion, which has a 3 minus charge. One of the polyatomic ion you have to memorize. All right, arrow, I'm just going to slow it down because I don't have space there, will give me 3 NaF. So right now I'm looking at this, meaning I need 3 Na plus aqueous plus 3 fluoride anion, right? And last, remember, if it's an insoluble salt, you leave them as it is. Do not touch it. And that's how you write down the complete ionic equation. I believe the challenging part for all the students is this, where you see this, oh, Na3PO4, right? Watch out for this. This is where the student miss this numerical coefficient. If you do not have those numerical coefficient, the charges and the number of atoms will not balance out, right? So take your time to go through this. Make sure you understand this. So I have my complete ionic equation. The last step to write down the net ionic equation is basically canceling out the common terms, if you want to call it, right? So the reactant side has 3 Ag plus. I don't see any Ag plus here. I do have 3 F minus here, 3 F minus aqueous cancels out. 3 Na plus aqueous, 3 Na plus aqueous cancels out. I don't see anything that cancels out, right? That means Na plus and F minus are my spectator ions. So if I ask you what are the spectator ions, your answer is going to be Na plus ion and F minus ion is going to be my, or are going to be my spectator ions. The last step is whatever is left is going to be your net ionic equation. Phosphate aqueous giving me Ag3PO4. Now, if you cancel out and write down the total ionic equation correctly, for your final one, the balance and the charges, everything will be balanced out as well. Look at that, you can double check, right? So this is a PO4, 3 minus. So that's how you figure out number one. Let me work to number two really quick, and number three you can try to yourself, which is sodium fluoride plus ammonium sulfate. Sodium fluoride plus ammonium sulfate. Sodium fluoride, it's a soluble salt. All right. Ammonium sulfate, also soluble. And make sure you know how to write down the chemical formula. All right. I do the exchange of partner. I'm going to end up with ammonium fluoride, which is also soluble in water. And finally, I have sodium sulfate, which is also soluble in water. Next thing I do is I balance my reaction. All right, I need 2 of ammonium on that side. I need 2 ammonium, and then I need 2 fluoride now, 2 sodium, and that is why that should balance the reaction. And again, remember, whenever you are balancing the reaction that has polyatomic ion, treat them as one unit, right? Do not try to break this into, oh, how much nitrogen I have, how much hydrogen I have. No, no, no. NS4 is a polyatomic ion, treat this as one unit. Since I need 2 of this ammonium ion, that is why I put 2 in front here, all right, and so on. That's my thought process. This is NS4, so that you see it clearly. All right, now it looks like, but then everything is soluble here, right? I did not form any precipitate. So if you look at the roadmap, it tells me if neither product will precipitate, write no reaction after the arrow. So all I do is tell my audience that there is no reaction. Right? Or what it's explicitly telling you is after you write that out, right? This writer should not be written as this, it should just be written as no reaction. Because we're not forming any precipitate at all. That's what they are telling you. All of these are going to be in their dissociated form, right? In their cationic and anionic form is clear solution, right? That's why there's no reaction, no gas that has been produced. All right. All right. So this is it. Hopefully make sure you watch this video. Again, like I said, if you are not watching the video, you are going to fall behind in class. Summer moves really fast at a very brisk pace. And then whatever is left, I'm going to finish doing the next lecture.